In part 2 of this lesson, we are going to look at the different spatial arrangements and shapes that organic molecules can adopt. These spatial arrangements are called conformations. The conformations of molecules are particularly relevant in organic chemistry, as they play a crucial role in understanding the behavior of molecules, especially in terms of stability, reactivity, and physical properties. Conformations refer to the different spatial arrangements, or shapes, that a molecule can adopt due to the rotation of its single bonds. Molecules are not rigid entities. Rather, they can undergo various rotational motions around their bonds. These rotations lead to different arrangements of atoms in space, resulting in different conformations. An example of two different conformations of a hypothetical molecule is shown below. In the first structure, notice the groups A and B, which are highlighted in red. Because of rotation about the sigma bond, we can imagine a number of possible orientations in which the groups A and B have various spatial relationships with each other. To describe these spatial relationships, we can use the geometrical concept of the dihedral angle. In organic chemistry, the dihedral angle refers to the angle between two intersecting planes, as is shown in the following graphical diagram. The Greek symbol theta is often used to represent the dihedral angle between two atoms. In the first structure, we can see that the two groups, A and B, have a dihedral angle of 0 degrees. Rotation about the sigma bond can move these two atoms in such a way to give other angles. Notice that when the two groups are 180 degrees apart, they have reached their maximum dihedral angle. These two structures, and any others that show the various ways in which the groups can be arranged in space, are conformations of the molecule. The analysis of these structures is called conformational analysis, and we will learn the fundamentals of this technique in this part of the lesson. The aim of conformational analysis is to determine the energetically favorable conformations of a molecule, and to understand how these conformations affect the molecule's properties, such as stability, reactivity, and biological activity. Conformational analysis uses several visual tools, including sawhorse projections and Newman projections, to inspect the conformations that are available and to consider which are more energetically stable. Sawhorse and Newman projections are frequently used to represent the three-dimensional structure of a molecule in 2 dimensions. In a sawhorse projection, the molecule is viewed along the axis of a specific bond, and the atoms and groups attached to the carbon atoms on either end of that bond are projected onto the plane of the paper. The bond itself is represented as a line, and the atoms attached to each carbon are shown as circles or dots. Newman projections are another common method used in conformational analysis. Let's go to the next slide to see how to interpret, draw, and analyze them. In a Newman projection, the molecule is also viewed along the axis of a specific bond. However, the point of view taken is directly down the bond axis, rather than partially offset, as in the sawhorse projection. In the Newman projection, the front carbon is represented as a dot. Because the back carbon would be covered by the front carbon, from this perspective, a circle that is drawn around the front carbon is used to represent this obscured carbon. To see how this works, let's draw a Newman projection using the following skeletal structure as an example. Before we start drawing, notice that the parent chain in this example is butane, and we have substituents at C2 and C3. To draw the Newman projection, we need to know the bond we will be sighting down. In this example, we will be looking down the bond that connects carbon 2 and 3. We also need to know from which perspective we will be viewing from, so that we know which atom is in the front and which is in the back. In this example, the perspective is indicated by the inclusion of the eye graphic, which tells us both the bond we are looking down and which of the atoms of this bond are in the front and back. carbon-2 will be in the front, and carbon-3 will be in the back. To start our Newman projection, we make a dot for the front carbon atom. Next, we need to draw 3 lines, representing 3 bonds. These 3 bonds are to each of the 3 atoms on the C2 carbon. From the perspective we are using, these 3 bonds are oriented in a Y-type shape, where we have 2 bonds placed on the upward-facing arms of this Y. The third bond is pointing downwards. Now we need to determine which atoms are connected at each of these 3 bonds. Looking back at the example structure, we see that some of the bonds are drawn differently than just simple lines, like those we have normally seen. These are called wedge and dash-style bonds. In organic chemistry, wedged and dashed bonds are used in structural diagrams to indicate the 3-dimensional arrangement of atoms or groups around a central atom. A wedged bond, which is drawn like a solid triangle connecting 2 atoms together, looks like this. A dashed bond, which is made from a series of hashed lines connecting 2 atoms together, looks like this. What do these drawing styles represent? Wedges are used to represent bonds that protrude out of the plane of the paper, or screen, toward the viewer. When you see a wedge, it indicates that the atom, or group, attached to the bond, is coming out towards you, essentially popping out of the page. Dashes, on the other hand, are used to represent bonds that extend into the plane of the paper, or screen, away from the viewer. When you see a dash, it indicates that the atom or group attached to the bond is going away from you, essentially receding into the page. With this notation in mind, we can translate the wedge and dash drawing into the Newman projection. Looking at the wedge-dash drawing, let's consider the spatial relationships of the atoms connected to carbon C2. We see there are 2 atoms attached to bonds that are wedges and dashes at this carbon: the bromine atom on a wedged bond, and a hydrogen atom on a dashed bond. Because the wedged bond is protruding out of the page, that would mean that the bromine atom would be attached to the bond pointing towards the right in the Newman projection. The bond pointing to the left, in the Newman projection, would be attached to the atom receding into the page on the wedge-dash drawing. This would be the hydrogen atom. The bond pointing down in the Newman projection corresponds to the bond pointing down in the wedge-dash drawing, and the methyl group is attached to this bond. This completes the front carbon atom. Now we need to complete the carbon atom in the back. We use a circle, drawn around the front carbon, to represent the carbon in the back. From the perspective indicated, the 3 bonds on this rear carbon would be oriented as an inverted Y. So there would be 2 legs, one on the left and one on the right, and one head pointing upwards. Looking at the wedge and dash drawing, we can see the hydroxy group, that is the group with the OH atoms, is on the downward dashed bond. The bromine is attached to the wedged bond, which is also pointing down, and a methyl group is on a plane line, as an upward pointing part of the zigzag drawing. Because the hydroxy group is on the dashed bond, it would be receding away from the plane of the screen, or page, on the 2 legs of the inverted Y. On our Newman projection, this means it would be on the bottom left. The bromine atom, on the other hand, would be on the bottom right, and the methyl group would be pointing upwards. Now that we have seen how to draw Newman projections, let's look at how they can be used in conformational analysis. Recall that the dihedral angle, represented by the symbol theta, is used to describe the separation between 2 groups that are attached to adjacent atoms. This angle is also sometimes called the torsional angle. Newman projections allow us to easily see the dihedral angles between various atoms within a structure. As a first example, let's look at the conformational analysis for the molecule ethane. To work on this exercise, it is recommended that you use the molecular model kit that was suggested for this course. Construct a molecular model for the molecule ethane. Your model should look like the one shown here in the photo. Ethane has 2 carbons, C1 and C2. There are 3 hydrogen atoms attached to each of these carbon atoms. If we sight down the bond that connects C1 to C2, we would see a view similar to the Newman projection drawn here. Using your model, observe that you can freely rotate the back or front carbon atom with respect to one another. These different rotations are called conformations. On the next slide, we are going to look at how the potential energy of the ethane molecule also changes as a result of these rotations. The diagram below is a graphical plot that shows how the potential energy of the molecule ethane changes when we rotate one of the carbon atoms with respect to the other. On the y-axis of the graph, we can track the amount of potential energy in the molecule as it changes. On the x-axis, we can track the dihedral angle between 2 hydrogen atoms, one attached to C1 and the other to C2. The hydrogen atoms we are comparing are highlighted in red on the diagram. We will start on the left-hand side of the diagram. The conformation shown here has the 2 highlighted hydrogen atoms oriented in a 180-degree dihedral angle with respect to one another. Notice that in this conformation, none of the hydrogen atoms on the front carbon are overlapping with the hydrogens on the back carbon. This is called a staggered conformation. In staggered conformations like this one, any rotation around the sigma bond connecting C1 and C2 will begin to narrow the dihedral angles between the hydrogen atoms. As these atoms get closer together, the potential energy of the molecule increases, eventually reaching its maximum point. Notice in the Newman projection that this maximum point in energy corresponds to the conformation in which all of the hydrogen atoms are overlapping with each other. This is called an eclipsed conformation because the bonds and atoms in front are covering up the bonds and atoms in the back. How has the dihedral angle between the red highlighted hydrogen atoms changed? Originally, these 2 atoms were 180 degrees apart in the staggered conformation on the left. Now we have moved these 2 atoms closer together by 60 degrees. The dihedral angle between them is now 120 degrees. As we continue to rotate carbon C2 around the sigma bond, we note that the potential energy oscillates between 2 different points, a maximum point and a minimum point, as the dihedral angle changes. The maximum potential energy in ethane is observed when the molecule is in one of the eclipsed conformations. The minimum potential energy, on the other hand, is observed when it is in a staggered conformation. When the conformation is eclipsed, there is an energetic strain present in the molecule. This strain is called torsional strain. Torsional strain, also known as torsional stress, refers to the stress or strain experienced by a material when it is subjected to twisting. In organic chemistry, torsional strain refers to the energy penalty associated with the eclipsing of bonds in a molecule. This strain arises because the atoms or groups involved are forced into higher energy conformations where their electron clouds overlap more than in the lower energy staggered conformations. This overlap leads to destabilization of the molecule and an increase in its potential energy. By comparing the potential energy difference between the staggered and eclipsed conformations for ethane, which is 12 kilojoules per mole, we can determine 2 important quantities. First, it allows us to estimate the energy cost that occurs when one hydrogen atom eclipses another on adjacent atoms. This energy cost, as mentioned previously, derives from the repulsive forces between the bonding electrons. Second, it allows us to estimate the population of molecules, as a percentage, that we can expect to be in either conformation at any given time, and at various temperatures. For example, at room temperature, less than 1% of ethane molecules will be found in the eclipsed conformation, as almost all will be in the lower energy staggered conformation. This information is helpful, because it means we can predict, on other molecules, the spatial orientations of atoms. In the conformational analysis of ethane, all of the eclipsing interactions were between atoms of the same type and size. We might ask ourselves what we would expect to happen if we replaced one of the hydrogen atoms with something else, say for example, a methyl group. Let's go to the next page and see. When we replace a hydrogen atom on ethane with a methyl group, the compound becomes propane. Let's look at propane's line bond structure to see how it can be transformed into a Newman projection for conformational analysis. Propane has 3 carbon atoms, which we can draw as a V shape using our line bond zigzag style drawings. Let's call these 3 carbon atoms C1, C2, and C3. To make a Newman projection, we need to sight down one of the carbon-carbon bonds in the structure. Let's pick the bond that connects C2 to C3. When we sight down the C2, C3 bond, we are looking directly at the C2 carbon, which is in the front of our Newman projection. We can represent this front carbon with a dot. The C3 carbon, which is behind C2 from our perspective, is represented with a circle, which is drawn around the dot that represents C2. This is the start of our Newman projection. Now we need to draw the other 3 bonds, at C2 and C3. Starting with carbon C2, which is in the front, we see that from the perspective we have chosen, that the methyl group attached to C2 is pointing up, and 2 hydrogen atoms are pointing down. One is on the left, and the other is on the right. This is the inverted Y configuration we saw earlier. On C3, the carbon in the back, we have 3 hydrogen atoms. Let's place these hydrogen atoms in a staggered type conformation, relative to the atoms on C2, as that would be a good place to start our analysis. The Newman projection we have drawn corresponds to the first conformation shown in the dihedral angle versus energy plot graph, shown here. The graph shows how the potential energy changes as a function of the dihedral angle. We see the same situation that we observed with ethane, namely that 2 energy states emerge, a high energy state and a low energy state. The low energy state occurs whenever we have a staggered conformation, whereas the high energy state corresponds to eclipsed conformations. When rotation around the sigma bond occurs, the methyl group and the hydrogen atoms on the carbon C2 in the front move closer in space to the atoms on carbon C3, and the potential energy increases as a result. Notice that the energy difference between the staggered and eclipsed conformations in propane are 14 kilojoules per mole versus only 12 kilojoules per mole in ethane. Why is there a difference in energy in the staggered and eclipsed conformations in propane when compared with ethane? Let's go to the next page and find out. We just observed that the barrier to rotation for propane is 14 kilojoules per mole, which is 2 kilojoules per mole more than for ethane. The increase in energy is the direct result of the large electron cloud around the methyl group and the corresponding increase in repulsive forces between electrons. Because we know that the energy cost of a single eclipsing hydrogen interaction is 4 kilojoules per mole, and that we have 2 of them in any eclipsed conformation of propane, we can subtract this cost from the total. The result is 6 kilojoules per mole, and we can conclude that this is the energy cost for a methyl group eclipsing a hydrogen atom. Through this type of analysis, the conformational energy costs associated with many different atoms and functional groups, in various spatial relationships, have been established and documented in the literature. Chemists use this information to plan syntheses and design molecules with specific conformations in mind. Now that we have looked at the conformations of ethane and propane, let's consider the next alkane in this series, butane. Notice that the Newman projection for butane has a methyl group on the front carbon, and also one on the back carbon. That's because we are sighting down the carbon-carbon bond between the C2 and C3 atoms. Notice that as we rotate the atoms around this bond, two different types of staggered conformations emerge. In one of the staggered conformations, the methyl groups are 180 degrees apart. In the other staggered conformation, the methyl groups are 60 degrees apart. These two different staggered conformations have two different energy levels. They are both lower in energy than any of the eclipsed conformations, but the conformation where the methyl groups are 60 degrees, instead of 180 degrees, is higher in energy. Additionally, there are two distinct types of eclipsed conformations. The highest energy eclipsing interaction shows that the two methyl groups are eclipsing each other, while in the second type, we see that the methyl groups are eclipsing hydrogen atoms. The type of strain that we are seeing in each of these cases has to do with the size of the groups that are near one another in space. This type of strain is called steric strain, and it introduces significant rotational barriers for the conformations of molecules. When two groups have a 180-degree dihedral angle, we describe them as anti to one another. As an example, in the lowest energy conformation of butane, the two methyl groups are anti to one another. This angle is the maximum possible separation of the two methyl groups, and this is why the staggered conformation with the methyl groups anti is lower in energy. There is an energetic barrier of rotation, caused by the steric repulsion of the two methyl groups. When two groups have a 60-degree dihedral angle, there is a steric repulsion called a gauche interaction that occurs. While these conformations still have less torsional strain, because they are staggered, not eclipsed, the gauche interaction introduces steric repulsions that are not present when the two groups are anti to one another. Now that we have discussed the conformational analysis and shapes of some fundamental alkanes, let's move on to our next topic, the structures and conformations of cycloalkanes. Many cycloalkanes, like cyclohexane, cyclopentane, and cyclobutane, are not perfectly planar due to the presence of strain that would result from being flat. Instead, most cycloalkanes adopt non-planar conformations. For example, if cyclobutane were to adopt a planar conformation, the bond angles in the ring would be forced into a 90-degree angle, which would introduce significant strain. This type of strain is called angle strain, because it involves the strain that results when bond angles deviate from the ideal tetrahedral angles of 109 degrees. To relieve this strain, cycloalkanes can adopt non-planar conformations where the bond angles and torsional angles can approach the ideal tetrahedral geometry. One way for measuring and comparing the stability for various organic compounds is by combustion analysis. Combustion analysis involves burning a known amount of a compound in the presence of excess oxygen and measuring the heat released. The heat of combustion is the amount of heat produced when 1 mole of a substance is completely burned in oxygen. For cycloalkanes, the heat of combustion can be related to their stability. More stable cycloalkanes typically have lower heat of combustion values because they release less energy when burned. This is because stable cycloalkanes have stronger carbon-carbon bonds, which require more energy to break during combustion. Therefore, by comparing the heat of combustion of different cycloalkanes, it is possible to infer their relative stabilities. Looking at the heats of combustion for various ring sizes, we can see that the stability of cycloalkanes generally increases with ring size due to the reduction in angle strain and torsional strain. However, beyond a certain size, other factors, such as conformational flexibility, may influence stability. Let's compare a few examples from this data. First, let's look at small cycloalkanes, specifically 3- and 4-membered rings. Small rings experience significant angle strain due to the deviation from the ideal bond angles. For example, cyclopropane with bond angles of approximately 60 degrees. Torsional strain is also high in small rings due to the eclipsing interactions between substituents. Consequently, small rings are highly strained and less stable compared to larger rings, which is evident in the much higher heat of combustion released per CH2 group in cyclopropane and cyclobutane versus cyclopentane and cyclohexane. These two cycloalkanes have released a minimum amount of heat, and so we would expect these rings to be the most stable. What is it about their structures that make these cycloalkanes particularly stable? 5- and 6-membered rings experience less angle strain compared to smaller rings because they can achieve bond angles closer to the ideal tetrahedral angle of approximately 109.5 degrees. Torsional strain is also reduced compared to smaller rings, leading to increased stability. 6-membered rings in particular are highly stable and commonly found in organic molecules due to their relatively low strain energy. As ring size increases beyond 6 members, angle strain becomes negligible as the bond angles approach the ideal tetrahedral angle. Torsional strain is further reduced in larger rings, contributing to increased stability. However, large rings may exhibit conformational flexibility, leading to potential strain arising from unfavorable conformations. Let's look in a little more detail at several cycloalkanes to get a better understanding of their three-dimensional conformations. While we commonly see the structure of cyclobutane drawn as a square, this representation is a little misleading. When all of the carbon atoms of cyclobutane are in the same plane, significant angle and torsional strain causes the molecule to adopt a more stable conformation that is not planar. This conformation is often described as puckered. The puckered conformation of cyclobutane is also commonly referred to as the envelope conformation. In this conformation, 3 carbon atoms and 1 hydrogen atom lie approximately in a plane, resembling the base of an envelope, while the 4th carbon atom is either above or below this plane. This deviation of 1 carbon atom from the plane of the other 3 carbons relieves the angle strain present in a fully planar conformation, allowing the bond angles to approach the ideal tetrahedral angle of approximately 109.5 degrees. The envelope conformation is more stable than the planar conformation because it minimizes the destabilizing angle strain present in the planar arrangement. Additionally, the carbon atom that is out of the plane experiences less steric hindrance from the other groups, contributing to the stability of the envelope conformation. Cyclopentanes are even more stable than cyclobutanes, and they are the second most common cycloalkane ring in nature, after cyclohexanes. Planar cyclopentane has virtually no angle strain, but an immense amount of torsional strain. To reduce torsional strain, cyclopentane adopts a non-planar conformation, even though it slightly increases angle strain. The lowest energy conformation of cyclopentane is known as the envelope, with 4 of the ring atoms in the same plane and 1 out of plane. Notice that this shape resembles an envelope with the flap open. The out-of-plane carbon is said to be in the endo position. Endo means inside. The envelope removes torsional strain along the sides and flap of the envelope. However, the neighboring carbons are eclipsed along the bottom of the envelope, away from the flap. At room temperature, cyclopentane undergoes a rapid bond rotation process, in which each of the 5 carbons takes turns being in the endo position. Substituted cyclohexanes are the most common cycloalkanes and occur widely in nature. A large number of compounds, including steroids, and many pharmaceutical products, have cyclohexane rings. The flavoring agent menthol, for instance, has 3 substituents on a 6-membered ring. Cyclohexane can adopt many conformations due to the size of the ring and its corresponding flexibility. What we observe experimentally is that cyclohexane is rapidly rotating between the two most stable conformations, known as the chair conformations, in what is called the chair flip, shown below. Several other notable, higher energy conformations occur during the transition from one chair conformer to the other. These are called the boat conformation, the twist conformation, and the half-chair conformation. Because the transition between chair conformations must proceed through each of these higher energy states, rotational and other energetic barriers can exist that favor one chair conformation over another, as we will soon see. Chair cyclohexane has neither angle strain nor torsional strain. This is because all carbon-carbon bond angles are near the 109 degrees tetrahedral value, and all neighboring CH bonds are staggered. Each of the other conformations, such as the half-chair, twist boat, and boat conformations, have either additional angle or torsional strain. In the images on this slide, we can see both a graphical depiction of the chair conformation, as well as a handheld model of a chair structure. At this point in the lecture, you should pause the video and construct a cyclohexane ring using your model kit. To do this, you will need to use 6 of your model kit's tetrahedral carbon atoms, which are usually black. These will have 4 pegs, or holes, depending on the kit style, for you to attach the various single bonds between carbon and hydrogen atoms. At each of the 6 carbon atoms, you should also attach 2 hydrogen atoms, which have a single peg and are white. Now that you have constructed a cyclohexane ring, you will need to twist and rotate the bonds around the rings to see if you can have it adopt the stable chair conformation. To know if you have reached this state, verify that the ring has 3 hydrogen atoms sticking vertically downward, acting like legs, helping the ring to stand on its own. There will also be 3 vertically pointing hydrogen atoms. It should look like the photo shown below. Now that you have constructed the model, keep it nearby. On the next several slides, we will explore several aspects of the conformational analysis of this model, how it can be represented in structural drawings, and how the various groups around the ring are described and change. Before we delve into the details for drawing a chair structure, let's take a closer look at how they are represented in drawings, and also learn to recognize the placement of bonds around the ring, and where they are located. First, let's look at just the carbon atoms within the ring, ignoring the hydrogen atoms attached at each one. Notice that when we draw a chair structure, there are 3 sets of parallel lines, and each set is directly across from one another. If this drawing were in 3 dimensions, like your handheld model, we would see that the 3 carbon atoms located here would be closer to us than the 3 carbon atoms located back here. To emphasize this, we sometimes use bold bonds, or wedged bonds, to help with showing the perspective of our view. Now, let's discuss the hydrogen atoms. Each carbon atom in a cyclohexane is attached to 2 substituent atoms. In cyclohexane, these substituents are hydrogen atoms. But we will also consider other substituents, like alkyl groups, in subsequent examples. Crucially, in a chair structure, all of the substituent atoms are oriented in a staggered conformation. It is this staggered conformation, which minimizes torsional strain, that makes the chair conformation so stable. How is this achieved, and how do we visualize this in structural drawings? Let's take a closer look. Upon examining the hydrogen atom substituents around the ring, we see there are 2 types of positions that are possible. To help better understand this distinction, consider the terminology used to describe the Earth's axis and equator. The Earth rotates around its axis, which runs through the north and south poles of the spherical shape. Similarly, a ring like cyclohexane also has a rotational axis that runs through the center of the ring. Axial substituents are those that run parallel with this axis. We can also consider the equator of the Earth, which is a plane that cuts through its center, dividing the Earth into a northern hemisphere and a southern hemisphere. We can also think about a cyclic molecule as having a plane that cuts through its center. Equatorial substituents are those that are roughly parallel with this equatorial plane around the ring. To summarize, a chair structure has substituents in axial and equatorial positions. Axial positions have substituents on bonds that are parallel with the axis of the ring, and there are equatorial positions, which are roughly in the plane of the ring. In the diagram of the chair structure, I have indicated all of the axial substituents in red triangles, and all of the equatorial substituents as blue circles. Notice that there are 6 axial substituents, and 6 equatorial substituents. Each carbon has exactly 1 axial and 1 equatorial substituent. Also notice that there are really 2 types of axial substituents. 3 of the axial substituents are pointing upwards, on the top face of the ring. The other 3 axial substituents are pointing downwards, on the bottom face of the ring. Notice that we see the same pattern in the equatorial substituents. There are 3 equatorial substituents that are pointing slightly upward, and 3 that are pointing slightly downward. Also notice that each carbon has 1 substituent pointing up, and 1 pointing down. For instance, on this carbon, which I am calling carbon 1, we see that there is an axial up substituent and an equatorial down substituent. If we go to the next carbon, however, we see that we have the opposite situation. We still have an up substituent and a down substituent, but the type of up and down have switched. There is an equatorial up here, and the axial is pointing down. If you do this same analysis around the ring, you will see this pattern continue. The axial substituents alternate between being axial up and axial down on adjacent carbon atoms. Similarly, the equatorial substituents also alternate between being up and down. On the next slide, we will learn how to accurately draw a chair structure and place the substituents in the correct locations. The chair conformation of cyclohexane can be drawn in 3 steps. Step 1. Start by drawing 2 parallel lines, slanting downward and slightly offset from each other. This means that 4 of the cyclohexane carbons lie in the same plane. The bond we have drawn at the top represent the 2 carbon atoms in the back of the ring, as shown here on a picture of a molecular model. The lower bond represents the 2 carbon atoms that are closer to us. These carbons are located here in the photo. Step 2. With the front and back carbon-carbon bonds drawn, we need to connect these 4 carbon atoms together, with an additional carbon on each side. To place these remaining 2 carbons, I am going to be drawing 2 parallel lines attached to the first 2 that we have drawn. These lines represent the bonds located here and here in the photo. Notice that when I am adding these lines, I am constructing shapes that look like 2 parallel letter L's that are laying on their sides. To make these letter L's, start with the bond at the top of your chair structure. These are the carbons in the back. You can see these 2 carbons located here and here in the photo. We need to make a bond that looks like it is pointing towards us, starting from the carbon atom on the back diagonal, that is pointing slightly upward, and moving diagonally towards the front diagonal. Once we have that first L drawn, we move over to the bottom bond. We need to make a diagonal line pointing upwards, in the direction of the back of the chair structure. This bond we are drawing represents the bond shown here in the photo. To make a good drawing, we want to try to draw these 2 L shapes, so that the lines are parallel both here, as well as here. In our final structure, we should have 3 sets of parallel lines. Step 3. Now that we have our L shapes, the last set of parallel lines we need to draw are the bonds that connect our L's together, to complete the ring. These 2 bonds are shown here and here in the photo. Now that we have drawn the ring of carbon atoms in our chair structure, it is time to add the axial and equatorial substituents to the ring. Let's go to the next page and learn how to draw the substituents with the correct orientations around the ring. We need to be able to identify and draw axial and equatorial bonds. We also need to be able to know when one of these bonds is pointing up or down. A very useful technique is to observe the direction that each of the carbon atoms in the ring is oriented. Notice that each carbon in the ring is pointing either upwards or downwards. For example, this carbon is pointing up, but the one next to it is pointing down. Notice that the direction each carbon is pointing alternates as we go around the ring. How does this help us know which direction to draw our bonds? It turns out that the direction that an axial bond will be pointing is the same direction that the carbon atom is pointing. For example, a carbon that is pointing up will have an axial substituent that is also pointing up. A carbon atom that is pointing down, however, will have an axial substituent that also is pointing down. If we draw in all of the axial substituents, notice that there are 3 on each face of the ring. There are 3 axial substituents pointing up, and 3 axial substituents pointing down. Notice that they alternate from up to down as we go around the ring. With the axial substituents drawn, we can now draw in the equatorial substituents. Remember that each carbon atom will have one substituent pointing up and one pointing down. This allows the ring to stagger all of the substituents and minimize torsional strain. So when we draw an equatorial substituent, it will be angled up or down. How do we know which way to draw the bond? If the carbon atom has an axial up substituent, its equatorial substituent will be angled down. If a carbon atom has an axial down substituent, its equatorial substituent will be pointing up. Also notice that the equatorial bonds are all parallel to the bond across the ring. Also notice that the 2 equatorial bonds at the carbon atoms in the central part of the ring are pointing to the outside, rather than the inside of the ring. They are also parallel with the carbon-carbon bonds that are at the 2 ends of the cyclohexane ring, located here and here in the structure. Recall that cyclohexane is rapidly interconverting between the 2 most stable chair conformations in what is called a chair flip or ring flip transformation. When a ring flip occurs, bond rotations cause all of the axial substituents to rotate into equatorial positions. Additionally, all of the equatorial substituents rotate into axial positions. We can see this transformation in the accompanying graphic. If we locate carbon atom 1, we can see a red bond representing the axial up bond. When the ring undergoes the conformational change into the ring flipped chair conformation, we can see the red bond on carbon 1 is no longer axial, but rather equatorial. Notice, however, that it is still pointing up. This is an important detail. When a chair flip occurs, all up-pointing axial substituents are converted into up-pointing equatorial substituents. If it was down axial, it will become down equatorial. The same is true for equatorial substituents. If one started off up equatorial, it will become up axial in the ring flip conformer. If it started down equatorial, it will become down axial. This transformation between axial and equatorial has implications on the stability of some chair conformations. We will see that axial substituents can introduce energetic barriers of rotation, making those conformations less stable than others. If we consider a mono-substituted cyclohexane, such as methyl cyclohexane, shown here, we can see how one chair conformation is far more stable than another, due to differences in the orientation of the substituent. At room temperature, methyl cyclohexane will be in the more stable chair conformation, where the methyl group is in the equatorial position, 95% of the time. Why is there an energetic preference for the methyl group to be in the equatorial position? In the axial position, the methyl group causes steric interactions that destabilize the conformation. Let's see how this works on the next page. When a substituent is in the axial position on a chair structure, a form of steric strain called 1,3-diaxial strain is introduced. This strain results from electron-electron repulsive forces between the three axial groups on the top and bottom faces of the chair structure. Also known as a flagpole interaction, the 1,3-diaxial strain increases as the size of the axial group increases. Larger groups cause more steric crowding, and this crowding does not occur when the group is in the equatorial position. As a result, a chair structure must overcome an energetic barrier to rotate into the conformations which place large groups in axial positions. The table below shows the energetic costs for various atoms and groups of atoms in axial positions on a chair structure. Notice that the size of the group strongly correlates with much larger energetic barriers. For example, when a relatively small atom, such as chlorine, is present as a substituent on a cyclohexane ring, the energetic barrier favors the chlorine in an equatorial conformation by approximately 2 kilojoules per mole of sample. What does this mean about the conformation we would expect to find the molecule in at any given moment? As shown on the table, in a sample of 1,000 molecules of chlorocyclohexane, we would observe the chlorine atom in an equatorial orientation in about 700 of the molecules in the sample. Only about 300 of the molecules in the sample, at any given moment, would have enough energy to keep the chlorine in an axial position before rotating into the more stable conformation. Compare the chlorine substituent with the much bulkier tert-butyl group. Because of the much greater steric hindrance to rotation, due to the large size of this group, only about 1 out of every 1,000 cyclohexane molecules, with a tert-butyl substituent in the axial position, would be observed at any given time. One interesting question to ask at this point is, what happens if there is more than one substituent on a ring? The answer to this question depends on several factors, which we will discuss starting on the next page. At this stage, it is important to clarify the use of chair structures versus wedge-style structures. We do not use wedge and dash notation on chair structures, because the three-dimensional relationships between substituents are shown using the axial and equatorial positions of bonds, as well as the chair structure itself. We do, however, use wedge and dash notation on cyclic compounds, when the ring is drawn as a flat skeletal structure. We use the wedge and dash notation on the flat skeletal structures to show the relative positions of substituents on rings. These drawings are limited, however, as they do not show the different conformations that are possible. For this reason, we need to be able to translate our wedge-style skeletal drawings of substituted cyclohexane rings into chair structures. Once we have the chair structure drawn, we can explore and analyze the conformations available. How do we translate the wedge and dash style drawing into a chair structure? When we look at the wedge and dash style drawing, note that we are viewing the structure from above. Because of this, all wedge bonds are pointing in the up direction. They may be axial or equatorial, but in either case, we can say that they represent bonds that are on the top face of the molecule. By the same token, we can also say that dashed bonds are pointing down. They represent bonds that are also either axial or equatorial, but they are on the bottom face of the molecule. What this means is that from any wedge-style drawing of a cyclohexane molecule, you can draw two chair structures, and both of them are correct. One of the chair structures you can draw may or may not be more stable than the other, but they will both be correct. As an example, consider the wedge and dash drawing of the substituted cyclohexane shown here. When we convert the flat ring structure into a chair structure, we need to draw the chlorine atom on an upward pointing bond to match the wedge. Suppose we choose a carbon, like this one, as the location on the ring where we will place the chlorine atom. Looking closely, we see that this location has two bonds we can use for substituents. Specifically, we see there is an axial up and an equatorial down bond that are available. Before we attach our chlorine substituent, let's label this carbon as carbon number 1. On carbon atom 1, which in this chair structure is an upward pointing carbon atom, the chlorine would need to be attached to the axial bond to ensure it is pointing up. Now we can draw the methyl group. To draw the methyl group, we need to move to carbon atom 2, which is the next carbon in the ring. Because the methyl group is on a dashed bond, we need to make sure that it is pointing down in the chair structure. To do this correctly, the methyl group must be drawn on an axial bond, on carbon number 2, because the axial bond is the only downward pointing bond available. Notice that if we had started by drawing the chlorine on a different carbon atom, such as this downward pointing carbon, we would have needed to use an equatorial bond. Why? Because at this carbon atom, the only upward pointing bond is equatorial. What would we do with the methyl group on carbon number 2? Because the methyl group is pointing down, being on a dashed bond, we would need to find a downward pointing bond at carbon number 2 in this chair structure. Notice that the only downward pointing bond at C2 is an equatorial bond. This is where the methyl group would be attached in this conformation. So, which one of these chair structures is correct? That's right, both chair structures are correct. These structures are the two possible chair conformations for this compound. Can you see which chair structure would be expected to be more stable? Exactly. The structure on the right-hand side, where the two substituents are both equatorial, rather than axial, is significantly more stable. This conformation avoids having any substituents, besides hydrogen atoms, in axial positions. This minimizes the destabilizing 1,3-diaxial interactions which we discussed earlier. To get some practice drawing chair structures, let's work on the following example. Pause the video and draw the two chair conformations that the compound shown here can adopt. When you unpause the video, we will compare these two chair structures and discuss which of them is more stable than the other. Now that you have had a chance to try this yourself, here are the two chair conformations for this compound. As you can see in this drawing, in each conformation we always have one of the alkyl group substituents in an axial position, whereas the other axial group is equatorial. In my first chair structure, for example, the ethyl group, at carbon number 1, is drawn on an axial up bond. This makes sense because it is drawn on a wedge in the flat ring structure in the example. The methyl group, however, is on a dashed bond on carbon number 3, meaning it must be pointing down on our chair structure. As a result, the methyl group is on an equatorial bond. The other conformation, however, reverses all of the axial and equatorial bonds. Notice, though, that the relationship between upward and downward pointing bonds is preserved when the ring converts into the other chair structure. This is why we see the ethyl group on an equatorial up bond and the methyl group on an axial down bond in the other chair conformation. So which of these structures is more stable? Exactly. The structure which minimizes axial strain is the one that places the ethyl group equatorial, not axial. Why? Because the ethyl group causes more steric strain than the methyl group. Having the methyl group axial is better than having the ethyl group in that position. At room temperature, we would expect the majority of molecules in the sample to adopt this structure, which has the methyl group axial and the ethyl group equatorial. As you have just seen, the relative orientation of substituents on cycloalkanes makes a huge difference in their structures and stabilities. Changing the direction a substituent is pointing in space can even completely change the identity of a compound. This phenomenon is called stereoisomerism. While there are several different types of stereoisomerism that we will learn about as we move through the course, the type we will focus on now is called cis-trans isomerism. When naming a disubstituted cycloalkane, use the prefix cis when there are two groups on the same side of the ring, and trans when two substituents are on opposite sides of a ring. The two compounds shown above, cis-1,2-dimethylcyclohexane and trans-1,2-dimethylcyclohexane, are stereoisomers. They have the same composition and the same connectivity of atoms, but they have different spatial geometries. Parts of these molecules are pointing to different places in space. This gives these molecules different physical and chemical properties. As you can imagine, this means that they also have different chair structures. Before moving on to the next lesson, you should practice drawing the various chair structures for these isomers using the problems provided in the homework exercises, as well as those from your textbook. That concludes Lesson 2. See you in the next lesson.